Hello and welcome to another episode of Golden Droplets. Let us start with some interesting facts about mining. Did you know what is the average time it takes to go from exploration to production? On average, it takes around 16 years from the discovery of a deposit to the start of the commercial production. This time frame can vary significantly depending on factors such as the mining method, the location of the mine, and the regulatory environment of the place. As an example, copper mines are usually faster. They take about 14 years to complete. Gold mines have slightly longer timelines, about 15 years, while nickel projects, for example, lateritic nickel projects, tends to take up to 18 years to develop. Some sources suggest shorter time of 7 to 10 years for projects with promising mineral showings. However, this estimate likely refers to the period after the initial discovery and does not include early exploration phases. Why does it take so long? Well, we were mentioning before the exploration phases. The exploration process typically involves several stages, including the grassroots exploration, the brownfield exploration, and then the on-site mineral exploration. Also, we have the environmental considerations. Actually, even before a mine opens for production, plans for the future closure and the land reclamation must be in place. And also the regulatory requirements. In many jurisdictions, environmental studies, permits, and consultation with indigenous community are required through the exploration and the developing of the process. Now, do you know what is the typical cost of developing a mine? And take into consideration that only 1 in 10 mineral exploration projects rejects the drilling stage, and only 1 in 1,000 drilling programs unearth valuable mineral deposits. The cost to develop a mine into production typically ranges from $500 million to over $2 billion, depending on the size, complexity, and location of the project. For instance, large copper or nickel mines often fall on the higher end because of the extensive infrastructure requirement. Let us talk about the time for profitability. After production starts, it usually takes from 5 to 10 years for a mine to become profitable. This time varies based on factors like market condition, the operational efficiency, and the nature of the commodity. Mines with high upfront capital costs, like those requiring significant infrastructure, may take longer to recover their investment. Let's see some typical examples. We have the Oyu Tolgoi mine in Mongolia. It's a copper gold mine that took over 16 years and an investment of around $6.75 billion before production started in 2021. Full profitability is expected after several years. Another example, Barrick's Pueblo Viejo in Dominican Republic. This gold mine cost around $3.8 billion and took over 10 years from exploration to production. It became profitable within 5 years after the startup. Then we have Cobre Panama, developed by First Quantum Minerals. The project took 15 years and around $6.3 billion in capital investment before beginning production in 2019. If we jump to Africa, we have the Kamoa-Kakula copper project, which took approximately 10 years. The development cost was around $1.1 billion, and they expect to be profitable in 2023. There are other examples for more efficient mines, but they are the exception of the rule. For example, the Cerro Verde copper mine in Peru, from exploration to production, roughly 6 years at a cost of $4.6 billion. And the time for profitability, it was achieved within 2 years of the expansion completed in 2016. Another good example is Fosterville gold mine in Australia, which took about 5 years with an initial cost of $30 million and became profitable shorter after production in 2016. Now, after hearing all this, some of you may wonder, Is there a better way to conduct an exploration program, something like the project in Australia? Well, yes, there is one. And I'm not talking about cutting corners or taking unnecessary risks. This is the subject of our presentation today. In this Golden Droplet episode, we will answer 3 questions. First one, where to look for the next deposit? Second, where to concentrate your exploration effort within your project? And finally, we will answer the very important question, how to find your next deposit. So this will be the subject of these Golden Droplets, so stay to the end if you want to shorten your exploration program by more than 50% and better use your exploration dollars. Until next time, enjoy! Where do we find our next deposit? For this, we're going to need to think outside the box. Today, we're going to be talking about where we can find our next deposit. And for that, I strongly recommend you this book, The Geological Methods in Mineral Explorations and Mining from Rogers Marjoribanks. This is a link to where you can find this book. And it's an excellent and modern book about exploration. And many of the ideas that I'm going to be discussing here, I took it from this book. So you probably have heard a lot about all the deposits have already been found. There is nothing to see here. Move along, people. There have been recent discoveries. Some of the factors responsible for recent discoveries are, first of all, people that search in unexplored areas like jungles or undersea or in the middle of the desert. Other people investigated weak anomalies or atypical mineral indicators that were previously ignored by the geologists. And in the specific case of the weak anomalies, I'm talking specifically about geochemistry, remember that you can have a weak anomaly because there is no gold or because the gold is very deep. So in geochemistry, it's very difficult to estimate the depth from where the signal is coming. And sometimes a new paper will come up with a new mineralogical description of the deposit, and that will give you an indication of another mineral indicator that you could use to do your discoveries. An easy way of recent discovery is just expansion of known deposit, and you all know the saying that the best place to look for a mine is next to a mine, and companies will drill around their deposit in the hope to find some blind or cover or deposit near the mine. A new geological model. Geologists come in with a new idea, a new interpretation of the existing data, and that will generate the possibility of discovering a new deposit. And finally, chance is always there. You probably all heard the story of the student that was taking some samples from a limestone, and he called the lab and said, well, I have some samples here, what kind of analysis I can do? And he didn't even specify that they were limestones, so the lab told them, well, you can do multi-element analysis, fire assay. So he ordered those assays. When the results came back, well, all and behold, there was gold, and that's how the Carlin type of deposit was discovered. There is also the story of the dentist in California that was driving and he lost control of his car. He came out to explore and he saw oil seeping out from the rocks. So chance is always a factor in discoveries of deposits. Now, what are your opportunities for new discoveries? Well, number one opportunity is the access to new information, being your own or public. And places like Canada, Mexico, many countries in Europe, England, they have geological surveys with a wealth of information that are available for free or at a very low cost, like in Mexico. You can go to any state in Mexico and buy all the geological map, geochemical data, geophysical data, satellite imagery, everything. And with that information, you can study it and get a new idea for a new discovery. A discovery in a nearby area. I remember I was working in San Juan, Argentina, in the Cordillera, very close to Chile. And by the time I was working there in Chile, on the other side of the mountains, they were making a big discovery, the Valedero deposit. And it was in the same area that I was, so I was in the right place at that time. A very important point is to get more experience by visiting other deposits. And of course, it would be great if we could all fly around, not even thinking about COVID, but having the money to fly around to different deposits and to see all these things. But there is an alternative. Many countries have these big mining conventions, like in Canada, the best one is the PDAC, Prospective Development Association of Canada. And in this conference, they have a section called the Core Shack, where every company will bring their core and, the best core for all different types of deposit. This is a wonderful and unique opportunity where you can just sitting in one place, visit 15, 20 deposits of all the world and get experience and get the eye for this type of mineralization, and then you can come back to your deposit and look it with new eyes. New technologies. An MMI was discovered. It had a great impact, especially in Australia, for the Australian regolite. Is very useful. More recently, we have enzyme leach, which for me is one of the best geochemical methods available, and the geophysics are constantly improving in their way of doing exploration. Besides that, you also have some technologies that are considered more academic, like isotopic analysis or fluid inclusions, and many others. And it's our job to bring those academic technology into the field, because they can really make the difference. They can open new opportunities for discovery. And finally, we have the political and or economical changes. And it works both ways. Sometimes there was a country that was not open to mining, and then they change the government, and the new president or prime minister say, oh, yes, I welcome the mining investors. Happened, for example, in Ecuador. There are places that they always have been pro-mining, like Armenia or Guatemala, which in their constitution is said that they want to develop mining. But you also have the reverse. Sometimes you were in a country and then they change the president or even the local government. Like there is a situation at this moment in one of the provinces of Argentina, Mendoza, where they cannot develop mining. The local government said no, they are against developing any kind of mining in that region, so you cannot work there. On the other hand, if India, which is #1 consumer of gold, announced several years ago that they will put a cap on the amount of gold that they will buy, the price of gold went down. And then China said that they want to buy more copper, and the price of copper went up. So you need to be aware of all the political and or economical changes and work with that. Now, you really need to be a critic. In order to get these new opportunities, you need to be a critic. So one of the things you will hear is, oh, this area is not prospective because it's covered by rocks X. And I had this personal experience. I was working for a company in Quebec, and half of the territory was covered by alluvial sands, pristine, white, clean alluvial sands. And of course, nobody's wasting their time working on that. But the company bought the satellite imagery for the whole area. And when I did interpretation of these images, I found that from below the sand, I was getting a very interesting signal for a porphyritic type of deposit. Now, the local geologists were completely against that. They said, oh, we have walked this thing, there is nothing there, these are just alluvial marine sands, there is nothing there. But I was fortunate enough that the president of the company was more open-minded, and they were doing aerial geophysical survey at the area, and they expanded into the sand, and they got the most beautiful geophysical signal of a porphyritic deposit coming from below those sands. So no, you don't take the area is not prospective as an answer. Well, number two, the area has been explored to the yin yang. Well, that may be, but that doesn't mean that there are not other opportunities. Sometimes the work that have been done have not been correct. Remember that many companies, they have like a plan. We do mapping, then geochemistry, then geophysics, then we do trenching, then we do drilling. And they apply that plan to no matter what. And there are deposits that will not respond to geophysics or will not respond to geochemistry. So you need to check, even in areas that have been explored very in detail. The area is fully covered by licenses. Well, this is true. There are places where you cannot find like 1 square centimeters of free space. If you go, for example, to Dominican Republic, the whole island is covered with licenses. But that doesn't mean that there are no opportunities here. First of all, if you have an area and for whatever reason you really want to explore that, maybe you have additional information or a new idea, a new geological model, etc. Well, you can always talk to the owner of the license and see you can buy the license from them or do a joint venture, etc. Especially in third world countries, most of the people that own licenses, they own this license for speculative purposes. They are not going to do any work there. They are just waiting for the opportunity like this one, that somebody will come and say, well, I want your area. There is also, in places like Chile, in Chile you can have a license, okay, and if I come and I want to apply on top of your license and you have not paid for the land, you have not done any work for many years, the ministry will contact the person, the owner of the license, say, well, you haven't done any work here, you haven't paid your license, will you pay? If not, I'm going to give this license to this other guy that is going to pay. There is also the possibility of applying to an area that is covered by a license, but for another metal. For example, let's say that somebody has a license for limestone, and you apply for the same area for possible Carlin type of deposit. That is admissible in most jurisdictions in the world. Then there is a special case that I have only seen in Colombia, is what is called the horizontal licenses that you can apply to the same area but at different elevations, which is a nightmare because at the end you're going to need to consolidate all these licenses into one. So you go back to point number one, talk directly to the owner of the license. Well, we don't have a good geological model that works in this area. That's another thing that you will hear. Well, first of all, sometimes the geology was misunderstood. And I have a perfect example of this thing. There are places where, for many reasons, most of the regional geology was done on the basis of interpretation of satellite imagery of aerophotos. And there is a place there that there was a river, and they have mapped an area as alluvial conglomerate associated to the river. And when we visited the area, we found out that it was not an alluvial conglomerate. It was an hydrothermal explosive breccia with copper mineralization on surface. So just by checking the geology, we could find this new deposit. Now, the last point is the area is protected. And this is a difficult one. And to tell you the truth, if the area is protected and you have other places where you can go and work, go to those other places. Because working in protective area is always a nightmare. It's very difficult. But if you really like your area, I mean, there is a huge potential, then first you need to determine what is the level of protection that you have. Even environmental have different level. If they declare the area park, then there is nothing to do there. But if they just want to prevent you to contaminate the basin, the hydrographical basin, there is like a buffer zone of 15 to 30 meters on both sides of the river that you just protect that area, and you can work on other places. And there are intermediate levels where you can do your exploration, but you need to do a lot of work to prevent environmental impact. With respect to the Aboriginal or local owners, it's not only a good professional practice, but it's a decent thing to do, is to discuss with them and see if there are ways to find a win-win situation to develop your area. Sometimes it's not possible. In that case, just go to the next area. So, what is your action plan? First, you need to formulate a task, your objective, what is called the hypothesis. Let's say I need to find a nickel laterite deposit for whatever reason. Then you determine what type of information you will need. For example, it is known that for nickel laterites, the best technique is just direct mapping. Also, geochemical sampling will work. Geophysics, no, there is not a good signal. Geophysics, sometimes they are a little bit more magnetic. Well, you can use magnetic to define the presence of ultramafic rocks in general, but the actual target of the laterite is not responsive to geophysics. And then when you have determined the type of information you need to explore what are the sources that you have at hand. And you will be surprised of how much information is available to you for free or at a very low cost. Many countries, they will have the geological funds. For example, one of the best places I have worked in my life in Armenia, they have one of the best geological funds I have ever seen. 50, 60 years of information from the Russian geologists that work in the area, absolutely for free, just to read and get the information right there. In other cases, there is a small fee to pay. You have geological surveys like Mexico, like England, like in general in Europe, Canada, the United States, in some states, that they provide an incredible amount of free or low-cost information. Like the USGS, there is plenty of information you can get for free. Then you have places like CEDAR, where all the companies are filing their technical reports. So again, a huge amount of information for free. And in general, the internet. So once you get your data, your job is to try to prove that your hypothesis is incorrect. And remember, this is the way science works, and we are scientists. In science, we don't try to prove that we are right, we are trying to prove that we are wrong. And if we are not capable of proving that we are wrong, then we assume that the hypothesis is good. But if we can prove that the hypothesis is incorrect, then we generate a new hypothesis and continue the process of trying to prove it wrong. So this is the end of the conversation. I hope these ideas will help you get a new vision on how to get this data and where can you find your next deposit, which could be right there where you are working. The presentations also include some sources and videos. To the left here you have a video from my colleague Dr. Vadim Galkin. He explains in detail all the theory behind the lineament analysis.
To the right is a little history of the work that we have done using lineament analysis. The process of discovery of a deposit is a very, very long one. So companies usually try to figure out ways of cutting the time. Normally you get to study data in a library, then you need to do the geological mapping, satellite interpretation, geochemical sampling, geophysical sampling, and at the end, drilling, which is one of the most expensive ones. One way some companies try to cut costs is to guess and to try to grab the cat by the tail. Usually Mother Nature will punish you for doing that. Let me tell you about a real case in Colombia. There was a company A that has a license and they did all the required work, mapping, geochemical data, geophysical interpretation. Finally, they find a zone, they drill it, and they find out a good ore zone. Next, a company that was located, that acquired license next to them, realized that, well, we can save all that. We know where the mineralization is coming from. So without any work, any geological or chemical sampling, they just start drilling, hoping that they will intersect the same mineralized zone that was detected by the other company. The reality was that between these two licenses, right at the border, there was a fault. And of course, the mineralized zone has shifted north. So all these holes done by this company were for nothing. They didn't intersect any mineralization at all. We have tested this method since 1999 in different types of deposits, metals, oil and gas, nickel laterites, and more recently in gemstones, emeralds and rubies, which is very interesting. So how does this work? First, we start with the selection of the area for the lineament analysis. Then we do a three-dimensional modeling and rose diagrams. Then we do the data processing and finally the graphical representation. While we have done more detailed lineament analysis on small areas less than 25 square kilometers. Usually the method works better when you have larger areas. 50, 100 square kilometers will be the minimum. One of the reasons is because a circular structure in a small area could look like a lineament, like a main lineament. So that will generate problems during the interpretation. The other thing is that you need to select an area, especially if you're doing three-dimensional modeling. You need to select an area that is larger than your current area of interest to avoid the deformation effect that gets around the borders of your area. Here we will be talking about 4 lineaments. Main lineaments, which are linear structures of more than 10 kilometers in length, secondary between 1 and 5, tertiary less than 1, and circular structures. If you want to do a little practice, please print this map out and we will draw some lineaments on it. You can start by drawing main lineaments that you can see here. So I will just look for structures that are in a line, in a direction. As an example, I have drawn here 5 lineament analysis. They are not all that they are, but just some examples of the most important main lineaments that you will find in this thing. Now try to find secondary ones. Again, I'm just showing here some examples of secondary ones. In the next step, we will try to find some circulars. As you can see, there is a couple of good circular structures here. So the next step is to combine all these lineament and to identify the points of intersections between them, between main, between main and secondary, secondary and tertiary, circular and secondary, all points of intersections. So the final step will be counting these lineaments. For that, we start by overlaying over this map a grid that could be 1 square kilometer or 500 by 500. It depends on the degree of detail that your client wants this work to be done. And of each square, you count how many main lineaments, secondary, tertiary, circular structures are, and the amount of intersection between them. Just as an explanation, I have included here 2 examples of this, of how we count. And I will tell you that at the beginning, we have now a software that does this for us, but at the beginning, for many years, we did this by hand. So it is possible to do, it just takes a longer time. Three-dimensional modeling include plastic and elastic deformation. A plastic model, we create a model with mud and sand, and on that model we trace the main lineaments. And then we subject this model to the different type of deformation, which are shown there with the different red arrows. And what is very interesting is that no matter from where the pressure is coming or the extension is coming, there will always be a group of faults that will open, and there will always be a group of faults that will close. Each experiment is repeated 2 or 3 times. Each result is photographed, and because we are looking for those places that will remain open for the most part of the time. At your left, you see the result of this experiment. In red are those places that remain open for most of the modeling. In blue, the ones that remain closed for more of the modeling. And why is this so important? Because really, geologists should be looking for spaces, for volume. It doesn't matter, you may have the most beautiful geochemical anomaly on surface, and it may be the result of a grain of gold that happened to fall in your sample. What you really need to find are spaces where a deposit could form. I use the analogy of a geologist is a person that goes into a kitchen trying to find a pan, a big pan, and the lights are off. So you have the option of going systematically, step by step with a match, trying to figure out where this pot is, or just go around and hoping to get lucky and find the pot. This method will tell you where the big pots are in your target. It doesn't tell you what is inside the pot. That will be done with the chemical analysis and geophysical, etc. But for at least it will allow you to reduce your area of exploration to those parts that really have the possibility of containing a deposit. The elastic modeling is faster. Instead of using a model made of mud and sand that every time you deform get destroyed and you need to redo it again, for the elastic modeling we use gelatin, where we mark the main structure. We use a polarized paper from below and a source of light, and when we do the deformations, you get the spectral deformation of the light, red being the more intense openings, blue being the more close environments. So it's the same method. We are looking for areas that will remain open most of the time, no matter from where the deformation came. Of course, if you are working in an area that you know for a fact that the area was subjected to a lateral compression, then you don't need to do all the models. You just model the ones that you know that works in your area of exploration. And then we use different softwares to represent this anomalies. And of course, the target will be that place where both the elastic and the plastic deformations indicate the higher values of deformation. This is your target. We have done this so many times, and I believe that the time that we were able to reduce the area for the lease was 50%. Usually we reduce the area by 60, 70%, even before you start working in your project. This is the type of study that you do before you put a foot in the ground. So it really allows you to concentrate your exploration dollars on the best targets, on the target that have the possibility of containing a deposit in a volume, in a space below the ground. The next step will be to add all other source of information that you may have. I must say that this technique will work just on the basis of a digital elevation model or a topo map, but it works much better when we can add layers of geology, geophysics, geochemistry, etc. The more information, the better. It is important that the areas that the type of data that you want to add are completely enclosed within the area of your study. You cannot use, for example, a biochemical data set that doesn't cover the whole area. This is a little trick that I use when I need to work with maps, hard copies that are not digitized, and it takes time to digitize a complex map like this. So it's very simple. You just open your data with Adobe Photoshop or GIMP to find the eyedrop util, and you just put the eyedrop on top of your image following a grid, and right here down at your right, you will get the composition of that area, which I usually put 3 by 3 pixels to cover a larger area as an average, and then I move it up, 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 and you will get a digital representation of your pixels. To do this integration, we use correlation analysis that allowed us to integrate all these different sources of information. The difference between our method and the hyperspectral method that you see here to the right, usually the hyperspectral method, they will have like 500 layers, and they say layer 30, 45, and 170. When you put them together, that will be montmorillonite. And those other three, that will mean quartz. Our method creates just one layer of information, a map that we call the prospective map. Another source of data is ROS diagrams, and this is something that can be done and usually done directly in the field, but how the problem was how to get that data into our system. And I created the flow chart that you will see here to your right that allows you to interpret each ROS diagram as a geometrical figure, and each geometrical figure has a value, so you get digital data that you can integrate and do correlation analysis and all the fact that we do with our analysis. Once you have all your data, you will get a table in Excel that will go from here to the next wall. It's usually very, very long. You have here the columns, UTMs, east, north, main, secondary, tertiary, all amount of intersection between main and main, main and second, main and tertiary, etc., 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 plus all the geophysical, geochemical, geological, ROS diagram data. So it really becomes a very, very large data set. After that, you start doing normal mathematical modeling, like determining the distribution law, eliminating hurricane or statistical outliers or hurricane values, and to prepare your data to do correlation analysis. And the correlation analysis allows you to create the figure that you will see here to the right, which is called a dendrogram, that represents the relationship between the different units the parameters that we are measuring. I forgot to say that once you have this data, the method works much better when you have within your target a known area of mineralization. In that case, if you have an area that you know that there is a type of mineralization that you're looking for there, you divide your data set in two. One that covers this mineralized area and one that covers an area that you know for a fact that is barren. And the objective is to get this coefficient, correlation coefficient, which I call the RCC, and that will be different for the mineralized zone than from the barren zone. So again, you will have the same amount, the same types of lineaments, no matter where, on top of the deposit or in the barren zone, but the relationship between these lineaments will be different, and that is what's going to help you map the define your next ore body. Another method that is very useful is factor analysis. The only problem with factor analysis that it's a mathematical tool that is very difficult to understand the geological meaning. So it's almost a try and test and see what you get and see if you can interpret it. But because it's a mathematical method, it has also the advantage that it's unbiased. So just use it also. As I mentioned before, instead of having 15 or 20 or 30 maps, even if you do additive anomalies, etc., you will get a lot of different maps. Here, with our method, you get one single map, which we call the prospective map. And that prospective map can usually be simplified just to determine the target's area. This is an example in Armenia, where the client had an area originally of over 500 square kilometers. We reduced that area to 4 main targets. So by 75%, we reduced the area. And all the work that have been done, exploration work that have been done in this area has been very, very successful. For most of our graphical representation, we use Surfer, but there are many other software available to do that. But the thing is, you can represent target areas here. To the right is a graphical representation of the Rose diagram. This is a real case study in Colombia in the area of Remedios from a company that have several mines in the area, which correspond to the, let me see if I can use this thing here. All the deposits are in this area here, and we found this new target zone for them, and they're currently exploring it. So here is a little bit of information about us. My name is Ricardo Valls. And for my good friend and colleague, Dr. Vadim Galkin, who is the brains behind this method. As I promised at the beginning, these are other sources that you can check to see, to learn a little bit more about the method. There are several companies that have filed their 43101's report on CEDAR, so they are public information, and you can find results of this method there too. And again, thank you very much for your attention, and we hope this presentation will help you find your next ore deposit.
And finally, we are going to talk about the complex system approach, which is the method that we use in order to save time and to reduce in more than 50% the time you spend doing
all the work that needs to be done in the field. So we take our time and organize the place before starting the sampling and mapping. As you see, our team is a big team. It's composed by 3 or 4 people. In this case, I have some students, and that's why you see more people. But this is the method. We get to the place, we find a good place to do the sampling and mapping, and we distribute the materials, the thing that we're going to use. So first, we're going to do the measurement of the pH. We can do this in the field, or another way of doing this is just taking the sample in the field, and then in the office or in the core shack we can prepare and do the whole processing of the data. I'm going to be showing, after this little video, I'm going to be showing another video where you can see samples being prepared on the camp, not in the field directly. So once we have the measuring the pH, we will determine the temperature, the range of temperature between the surface and the bottom of the hole. And this is a method which I call thermometry, and we don't have time here to explain, but it's one of the best mapping tools that we have at our hands. And usually this difference between the temperature will indicate areas that have mineralization. So they're showing the pH. Just remember that when you use the pH paper, you need to wait 7 seconds or so before doing the measurement. So we select a place to do the sample. We are using a technique that's the thermometry, measuring the surface, measuring at the bottom of the hole. That's it, very quickly. We are using a chemical technique called enzyme leach, which requires only a few grams, actually 2 grams is enough of material. But here I'm going to show you a way that we take this sample, and using a condom we will enrich the original material by 500 times or even more. One detail that you always need to check is the geobotanics indicator. What I'm holding in my hands there is a fern that is very typical for places with high contents of arsenicum, and is an indicator for gold deposits. So we were in a very good area to start with. So I'm explaining to the team how to use also our iPhones in order to record all the information. As I mentioned, we do everything in one pass. So not only we take a soil sampling, we also take lithology, and I'm explaining how to do a channel sample, and do a lot of geophysical measurements using basically our iPhones. But if you have geophysical instruments like a capometer or a radiometer, etc., you can also use those. The objective is not to return to the same place. It's funny, the people from Dominican Republic, they call this method not the complex system approach, but the Attila method, because after we pass through a place, there is nothing left. So here I am showing them how to take a heavy mineral concentrate, but this is applicable to everything, to a soil sampling or stream sediments or a heavy mineral concentrate. As you know, in a heavy mineral concentrate is a function of physics. Is either the water increase the velocity washing the light fraction, or the water diminish the velocity depositing the heavy fraction. So we need to check places in the river or in the creek where the precipitation of the heavy fraction was already done by Mother Nature. The areas of natural concentration of heavy fraction is usually marked by the presence of small conglomerates. So we will take the sample from the place where Mother Nature already did his work to concentrate the heavy fractions. Now, the method in general is as follows. We have a constant volume, which in our case is a plastic bottle, and we will fill that material, and we will fill that bottle with material taken from the best part from the river. We will make sure that we fill the bucket to the maximum capacity, and you can take sample from 2 or 3 different places. It's not necessary to take all from one place. So now that we have a volume, the next step, as you will see a little later, is to weight that sample. Weight by volume, that is density. So even right now, if that sand was rich in heavy minerals, it will be more heavy, the density will be higher. So here we are with the balance. We measure the weight of the plastic, okay, and then we weight the material. And as I said, weight by volume, that gives us density, which is a very good indicator, one of the things that we can make directly in the field. So what is the next step? The next step will be to sieve the material. We use a mesh -80, or like we need to define what is the macro fraction, okay, from the sample. So if you have a normal sieve from a kitchen, it will do the same work. So we use a plastic bag in order to homogenize the sample before taking the portion that we're going to use to do the concentration using a condom. So you can see we're using a little bit of water too. Remember not to use any rings or jewelry. Okay. Once we have the fine fraction on the back, we will weight the macro fraction too, so we can later estimate what is the percentage of macro fraction to micro fraction in the sample. And we will start the process of homogenization, and this is done very simple by pulling up and down the plastic bag, as you will see in this video. We are decanting the excess of water, okay? It's mud. We are not losing anything there. Now, pay attention to the way we do the homogenization. First, I push it up, and he does the same thing. So it will rotate, not slide, but it needs to rotate in both directions. So that way we are homogenizing the sample, and we repeat the same thing, but laterally. So that way the material has been concentrated and very well mixed at the bottom. Next, we're going to use a condom to obtain the heavy fraction. It's like doing a heavy mineral concentrate, with a pan, but with a condom it takes less materials and about 10 seconds, 15 seconds to get the perfect sample for the lab. If you're going to use a condom, please look for one that doesn't use oil. The cheapest, the better. Or you can use also a balloon or a finger from a glove, anything that has that position. Okay, so we are doing this in the field directly, as I mentioned, and I'm going to show you later. In Dominican Republic, we established this method to do it directly at the office. So in the field, they just grab the sample, they do the measurements, and then this part, they do it in better conditions in the office. You can see there, we are putting the material into the condom. We lost a little bit there, but that's clay, nothing heavy. Now, once the material is inside the condom, it is very simple. Just grab the top, close it, and do a vertical movement. We call this practicing safe geology. And in just a few seconds, as you can see, at the bottom, all the heavy material have been concentrated, and on top is just clay and the light material. So you just grab the end and throw away the rest, and that is your sample. At this moment, the labs will take the sample right from there. So no more manipulation need to be done. Here at the beginning, we were taking the sample out of the condom, put it in a paper bag, and then send it to the lab. But the labs now knows what we are doing with this, and they will receive the sample in the condom. So this method, and we have data to prove, enriches the original sample minimum by 500 times. So just imagine what you're doing. You are eliminating all the clay, all the limestone, all the mineralization, all the material that has nothing to do with the mineralization, and you're concentrating the mineralization at the bottom of the condom, which is the sample that the lab will take. Okay, so that is it. Let me show you now how this is done in an office.